Hi everyone, I'm trying to create this brief video to help you out with the lab today. Cardiodynamics is complicated because we have to think about what the heart is doing and we have to think about the timing of the heartbeat. So I want to quickly review what's going on in the left ventricle because that is really what determines cardiac output. And just keep in mind the left and the right ventricle pump the same amounts of blood. We focus on the left because we're just thinking about the systemic circulation for now. We're also going to talk briefly about the electrocardiogram and the amount of time the heart spends in systole and diastole. And I'm talking about the ventricle now when I say the heart. So let's review stroke volume and cardiac output. I hope everybody remembers that cardiac output is the amount of blood pumped by the heart per minute. And that's influenced by heart rate and stroke volume. So heart rate times stroke volume equals cardiac output. And if we look at some typical values, we know that heart rate in most of you is right around 70 beats per minute. And we know that your stroke volume is right around 80 milliliters per beat. So cardiac output is going to equal 70 beats per minute times 80 milliliters per beat. And that's going to equal to 5,600 milliliters per minute. Now that's also equal to 5.6 liters per minute. And that's really the cardiac output that you probably already know. It's right around 5 liters per minute in most of us at rest. Now cardiac output is highly variable and it really depends upon the status of your autonomic nervous system, so your sympathetic and parasympathetic tone. And it also depends upon homeostasis and the call from the tissues for more blood. So when you're doing work, when your tissues are metabolically active, you need more oxygenated blood and cardiac output will increase. This lab is all about how that happens, and it's about you getting a feel for about how much heart rate increases, what happens to stroke volume, and how these two variables balance to result in an efficient and a sufficient cardiac output. So what controls cardiac output? We've talked about heart rate. We've also talked about stroke volume. You should remember that heart rate is primarily controlled by the SA node, and the SA node is influenced by the parasympathetic nervous system via acetylcholine, which has an inhibitory effect, and by the sympathetic nervous system, which through the neurotransmitter epinephrine can stimulate heart rate. So epinephrine can depolarize those cells in the SA node and increase heart rate. Now the nervous system, specifically the autonomic nervous system, also influences stroke volume. So we know that epinephrine can stimulate stroke volume by increasing contractility. What that means is for every heartbeat, the heart contracts more powerfully. Now here's arguably the hardest part. Stroke volume is controlled by end diastolic volume. And if you can remember, end diastolic volume is that volume in the heart at the end of diastole. So it's really the maximum volume of the ventricle. On the last slide we saw it was 130 milliliters. End diastolic volume is controlled by venous return. It's controlled by the amount of blood that returns to the ventricle. So the left ventricle receives blood from the pulmonary vein, and the amount of venous return is really going to influence end diastolic volume, and that has a direct influence on stroke volume. So you know if you put more blood into the heart, it pumps more blood out. Right? That is a law of the heart that says if you stretch it, it contracts more powerfully. Let's go to the next slide. Here we can see exactly what's going on with the heart. During diastole here, that ventricle is filling, correct? So this represents an entire cardiac cycle, and during that cardiac cycle, we're at rest about 2/3 of the time, and for about 1/3 of the time, we're in ventricular systole, which I'm marking in red. So this is when that ventricle is ejecting blood. Here is when the ventricle is filling. And right here is the most important time. And we're going to talk about that repeatedly. So now stroke volume is equal to the maximum volume of the heart, or EDV, minus the minimum volume of the heart, or ESV. So clearly increasing EDV, increasing stroke volume, and just as clearly decreasing ESV will increase stroke volume. Now I keep talking about filling time, and I don't want to overdo it, but when we increase heart rate, when we double or triple it, we reduce the amount of time that we have here in ventricular diastole. When the heart rate increases, diastole is shortened proportionally more than systole. And what that means is if we decrease by half the amount of time that we have for filling, look what happens. We only get about, what would you call that, 100 milliliters? So stroke volume would equal 100 milliliters minus 50 milliliters. And that's equal to 50. So we've decreased stroke volume. That's going to have a negative influence on cardiac output. However, we're beating more times per minute. So really what happens as heart rate is massively increased, the heart pumps rapidly, but for each pump we only get a little surge of blood. So it's a balancing act in between having a really robust stroke volume and a slower heart rate with having a really fast heart rate and a small stroke volume. And it's different for different people, and it's different depending upon how well trained you are. Okay, what about the electrocardiogram? Remember, we have ventricular diastole, that's most of the time, and we've got ventricular systole for a short amount of time. So if we have a cardiac cycle that typically lasts 800 milliseconds, this is the amount of time in systole. That's 240. That leaves a total of 560 for diastole. Now let's shorten this cardiac cycle to 400 milliseconds per beat. So now just imagine that we have really decreased this to 400 milliseconds. What that means is systole is going to be from here to here, and diastole is the rest. Systole does not decrease to 1/2 the time. So do you hear that? You cut the cardiac cycle in half, systole is going to be reduced from 240 to, let's say, 180. Which means that diastole, if we have 180, that means we're going to have 220 milliseconds for diastole. 220 milliseconds. So that has a strong effect, a strong reduction in EDV. So take-home message, for small changes in heart rate, there's no significant effect on EDV. For big changes in heart rate, EDV is limited. It's really shortened because filling time is shortened. Okay, that means you have to know the difference between small and big changes. A small change in heart rate might be going from 70 to 90 beats per minute. A big change would be going from 70 to 150 beats per minute. More than double. Okay? I hope this helps. Go through that case study and let's see how it goes. Have fun, everyone, and thanks for listening.